Hello, everyone. Welcome after the break and the poster session. We hope you enjoyed it and could get inspired. Welcome to the last keynote speech. I'm happy to present to you Alexei Efros, a professor of computer science at University of California, Berkeley, since 2013. His research in the areas of computer vision and computer graphics uh, is his main topic of interest. In the past few years, his lab has been at the forefront of reviving self-supervised learning, releasing many influential works, including Pix2Pix and cycleGAN. During the event, the professor will give the lecture about self-supervised visual learning and synthesis. Let's welcome the professor and enjoy the lecture. Professor, the floor is yours.
All right. Hello, I guess good evening, everyone. My name is Alexei Efros, and I'm very happy to be here, even though it is virtual. I have to say that growing up as a kid in the Soviet Union in the 80s, I always loved Polish culture, and I grew up on the poetry of Julian Tuwim, and I watched the Polish cinema and the wonderful Polish comedies, and I have a deep love for Polish culture. So maybe next time I will be able to come and visit in person. But for now, we'll do this virtually. So since it's the end of the day, I thought I would give you less technical and more of an overview talk about some of the work in self-supervised learning, particularly in computer vision. And really, the talk could be retitled as "It's all about the data," and I will hopefully show you what I mean. So, you probably, if you read popular magazines, it sounds like artificial intelligence is almost here. It's really we need to defend ourselves against computers who are out to take over. And maybe you also heard that deep learning solves everything, right? You don't need to program anymore. You don't need to code. All you need to do for any given problem is label some training data, define some objective function, train a neural network, and sell your startup for millions of dollars. In fact, I'm here in California, and that is exactly the steps are that a lot of people are taking now. Okay. And you probably heard about some breakthroughs, for example, performance on this task called ImageNet has been really improving. So we are now at about 80% correct classification performance. So given an image, it can give us the label for that image with 80% probability. There are other things like, for example, you can do planetary scale geolocation. Given an image, the computer can tell you where that image has been taken. Okay. Or you can do something like automatic image captioning. Again, another kind of popular topic. You give a computer an image, and then it writes a caption for you. And so you can see, for example, on the right-hand side, a group of people posing for a picture on a ski lift. This is quite amazing. This is really kind of magical, right? It's a group of people that's posing on a ski lift. So it seems like the computer is really, it has a mind of its own. It really gets everything right. Well, as the great bard has said, something is rotten in the state of Denmark, and I'll let me show you what I mean. Things are not as good as they may seem. So let's start with the last one, image captioning. So here is an image I got off the internet, and I send it through the image captioning software, and I got the following caption: a car parked on the side of the road. Okay, so this is actually pretty good. It's maybe it's the car is in the United Kingdom, or maybe in Australia, where they drive on the left side, so you park on that but it's still pretty good. Okay. But then what I did is I got a whole bunch of internet images of cars. And what you see is basically this caption works pretty well for essentially all of them, right? For almost all of them, a car parked by the side of the road is actually a pretty good caption. Indeed, then I thought, okay, what about something like this? And guess what? It's a car parked by the side of the road. What about this? Yep, it's a car parked by the side of the road. There is a car, there is a road, and maybe there is some side. Okay. Um, so basically, the issue here is that it seems like the computer might not be that smart. Maybe what is happening is that the computer is just getting, uh, finding a caption that has a car in it, and and just spitting out the the closest caption from the training set. Okay, so that's not what we really want. What about image classification? Again, performance on ImageNet, it's now up to 80% correct, which is pretty impressive. But the thing is that if you take this classifier and you run it on just a real world, you take a YouTube video and you just run it on a random video just walking around, the performance drops to about 30%, right? There's a huge drop. So what's happening here? Well, here is one example. It's one of my favorite classes. This is the T-shirt class in ImageNet, okay? And here are actual T-shirts in the real world, okay? Do you see that those two classes are extremely different, okay? Right? It's not really even fair for a computer to be able to try to find the T-shirts in the real world if all it has seen at training time are these very nice, segmented, clean, laid out T-shirts at training time, okay? So it's not really that surprising that it's not really getting this, okay? And this is true for many, many classes in ImageNet, that it's trained on very different distribution of data than what we have at test time in the real world. Okay. Finally, geolocation. This is a topic close to my heart because we did a work in 2008 called IM to GPS. And this was done, no deep learning. This is basically just very simple nearest neighbor. You get an image, you find a nearest neighbor in some feature space, and then you basically use that to vote where you are. Okay, and we had about 6 million images on that. This was one of the earliest paper with lots and lots of data, earliest big data paper. And then about a decade later, Google has returned back to this problem, and there of course they use the deep network, and they also had a lot more images. They had 91 million images because they're Google, so they can afford it. Okay, and the performance was much better. Okay, but notice that two things have changed. First, instead of nearest neighbor, they use the deep net. But the other thing that changed is that they use an order of magnitude more data. So what has what was the cause of the improvement in performance? The deep nets or the data? Well, luckily, the paper called Planet actually has a comparison with the same number of data points, apple to apple comparison. So you can see there's this IM to GPS new and Planet 6.8 million images. And there you can see that actually in that regime with the same data, the nearest neighbor algorithm is actually performing pretty well. In fact, for some regimes, it's doing better than the neural network, which is kind of surprising to a lot of people. Okay, so this kind of underscores a very important fundamental thing that sometimes we are maybe over over giving too much faith to the algorithm. So here is another kind of classic example from computer vision in the field of face detection. Face detection is one of the first things in computer vision that actually started working. I remember this. This was in the late 90s when I started graduate school, and you ask people, okay, what is the paper that made the made face detection work. Okay, and most people who has taken computer vision class will tell you the paper is called Viola Jones, 2001. But in reality, there were actually three papers that all got very good results. Okay, and they had very different features, and they had very different classification. So the first one was actually in 1998. That was the first paper. Their classifier was neural network, but back then neural networks were considered to be very old-fashioned, and so nobody cared. The next one that was actually had the best results of the three, 99, Schneiderman and Kanadi. Its classifier was naive Bayes, so kind of simple. The features were a little bit more interesting. And then there was Viola Jones. And the reason why everybody remembers Viola Jones is because it had a very cool novel classifier called the boosted cascade. And it was a beautiful, beautiful idea, beautiful algorithm. But people are forgetting that actually it wasn't the best performing. It wasn't the first, and it wasn't the best. Okay, and so there is a little bit of this kind of scientific narcissism that, all things being equal, we prefer to credit our own cleverness or our algorithm's cleverness with the success, where sometimes really what we need to credit is the data. Okay, because are we really that clever? Well, maybe not so much. So here is kind of one example from ImageNet classification using a neural network. So you have an image on the left, and then you ran it through a network, and then it tells you the label on the right, and it says, okay, it's a Shetland sheepdog. Okay, looks great. But what if we take the image and then we perturb it, kind of move around the pixels to make it, all the same pixels, all the same statistics, but make it not look like a dog, something like this. Okay, so kind of use the texture synthesis to move it or change it around. Guess what? The network is perfectly happy to also say that that's a sheepdog. This the same thing. This the same thing. So it looks like the network is not really looking for a dog in the way that we humans look for a dog. That, finding foreground versus background, finding the body, the head, etc. No, it's basically just looking at doggy texture, and using the doggy texture seems to be enough to solve the task. Okay, so it basically seems to be cheating. It seems like the classifier is not really doing what we expect it to do. Here's another example from the task of action recognition. So you have a video of somebody opening the fridge door, and then your task is to say, what is being shown here? Is it picking up cup? No. Is it slicing bread? No. Is it opening fridge? Yes. Okay. And again, the algorithm works really, really well, 99% accuracy. But when we look at what it's actually doing, it turns out it actually doesn't care about any of the kind of interesting things. Like it doesn't track the hand, it doesn't find the fridge door. Basically, all it's doing is looking at this one frame. It doesn't even need a video. It looks at this one frame of the texture inside of the fridge, and that's how it knows it's opening the fridge door. Okay, so this is worrisome. Okay, this basically means that a lot of the time this semantic supervision that we train our algorithms with, it leads not to reasoning, not to understanding, but it leads to memorization. It's a little bit similar to, I don't know how it is in Poland, but in America, you have in universities, you have a semester of classes, and then at the end you have a final exam at the end of the semester, right? And so what a lot of students do, uh, those who don't come to lecture, but then at the end of the semester, they go and they basically look at previous exams, and they just try to memorize. They try to memorize question, answer, question, answer, question, answer. It's called cramming. Okay. And the unfortunate thing is that it works really, really well. Because the exams are going to be similar. So you go to the exam, and chances are you will do reasonably well. I have done it myself when I was a student. Okay, it actually really works. But have you actually learned the material? No, of course you haven't learned the material, but you have done well on the exam. So it seems like what we're doing is we're raising a generation of algorithms that can only cram for this test set, but don't actually learn the material. Okay, and that is a problem. Okay, and so we can then step back and see, okay, how can we address this? And we can think back to, why do we actually have computer, why do we have vision? Why do we have human vision? Why do humans have vision? Okay, and see if we can start from the beginning. Well, the answer from somebody like Aristotle or David Marr, who is a kind of an early theorist of computer vision, the answer is to see what is where by looking. Okay, and that's a reasonable functional answer. Generations of computer vision scientists have thought about it this way, but it's a little bit unsatisfying, because then you still have the answers of why. Why do you want to see what is where by looking? And if you start asking yourself that question, you very quickly go down into this rabbit hole, and then eventually you realize the whole reason for all of this goes all the way back to Darwin and Dawkins. And the reason is to make babies who make babies who make babies, etc. Right? That's kind of because vision gives you an evolutionary advantage against species that don't have vision. Okay, so that's really the objective that we ought to be optimizing. But of course, we just don't have enough compute to do that. Okay, so we can think of something maybe in the between this whole, looking, what is where just because we think it's a good idea, and this ultimate, evolutionary objective. And a lot of people have been thinking about prediction as this kind of a reasonable task. Okay, so neuroscientists like Moshe Bar have been talking about predicting the world as a task that it seems like the kind of the meta task that everybody seems to be trying to be, all the algorithms are trying to do, and everything, the ability to see comes from this prediction task. And so we thought, okay, can we make prediction the kind of the fundamental task for our computer algorithm as well? Okay, and the nice thing about the prediction task is that we don't need to have labels come from a human. We can have the world itself serve as our supervision. So we can predict some aspect of the world that we interact with, and then, we can just see what happens. We can query the world. For example, what is going to happen next? Well, we wait a little bit, and that thing that was going to happen, either it happens or it doesn't happen. So that's a supervisory signal. Or we can say, okay, what's to my left? Well, I can make a prediction, then I can turn left, and then I can see if I was right or not. you know I can say, what can I touch? Well, I can make a prediction, then try touching it and see if it works, or what makes a sound, etc., etc. So you can see that now suddenly, instead of these semantic labels, cat, dog, couch, we now have labels that are given to us by the world. And this is fundamentally the idea of self-supervised learning. Okay, self-supervised learning is a paradigm where you're using the machinery of supervised learning, but the labels are given to you by the world itself rather than by the human. Okay, so you probably have heard of some of the kind of standard self-supervised methods. One of them is autoencoders. So the idea is that you want to get a representation for a high dimensional input like an image, and what you want is you want to compress it into some sort of a small vector, latent vector z. And one way to do it is you have a task which is a reconstruction task. So you reconstruct the image with a bottleneck, and that forces your compressed image vector z to be interesting. Now, this is an example of data compression. Okay, you're basically trying to compress this input x into some small vector. And compression is related to machine learning, but it's not the same as machine learning. Okay, because compression really only cares about the training set. It doesn't give you any guarantees for what happens at the test set. Okay. And so instead, there is a related task called data prediction, okay, which is a little bit harder. So you can't, it's not just compression. So here, you give some of the data as the input, and then your goal is to predict the other part of the data. So now it's not just compression. Now we need to work harder. And this is at the core of a lot of self-supervised methods. Okay. Uh, in kind of the idea of self-supervision actually comes early. Some early work has been in psychology and related disciplines, where the idea was to use self-supervision to model multisensory learning, for example, a vision and audio together. But now there is a lot of different self-supervised directions. Uh, the first, as I mentioned before, is basically just data prediction. Given part of the data, you try to predict the other part of the data. There is also a type called transformation prediction, where you have two pieces of data, and what you want to do is you want to predict what was the transformation that transformed the first part of data into the second one. And also, what I call meta supervision is where what you're trying to do is that you're trying to uh, transform the data to have some constraints. So you have constraints on the data. So your label are the constraints on the data, not the label of the data. Okay, and um, so I'm going to talk about some of my work in all of these three areas, and of course, this is the work of my wonderful students and postdocs, and I'm just here to tell you about all of their wonderful stuff. Okay, so first, self-supervision as data prediction. Okay, the simplest one. Um, you transform. You try to given one part of the data, you're trying to predict the other part of the data. One of the first works in that area was the idea of using predicting color from a grayscale image. Okay, so given a grayscale image, we train a network that predicts the chromaticity information. So in the LAB color space, given the L channel, we're predicting the AB channels. Okay, and the thing here is that the nice thing is that we can get infinite amount of training data for this. How? Well, we just download millions of images from the internet. They're all color images. Then we split the images into the L channel, the grayscale channel, and the color channels, and then we just use the gray as the X and the color as the Y, and then just train our network like this for many weeks. Okay, and it actually works pretty well. And the nice thing is that given the correct, if it works well, then you can actually, as a byproduct, you can actually colorize your grayscale image. And indeed, that's what we try to do in first. So this is some classic grayscale photographs, and we can make them color. Here's another example. Here's a color version. But of course, the interesting thing for us is not necessarily this. The interesting thing is, can the network inside, can it learn some sort of semantic information? Can it infer something, something about the structure of the world? Okay, and the answer seems to be yes. And the reason we found is that uh, here is some colorization examples that are kind of failures. Okay, but they're instructive failures. So if you see again, grayscale color. So what's happening here? There is a little bit of a mistake here, right? Look at this. Look at this thing. See this pink thing here, or pink thing here, right? Why is it pink? Well, it's pink because it thought that there would be the tongue would be out on these dogs, but the tongue is not actually out, right? The tongue is not visible, but it's still painted pink. Now, why is this instructive? Well, it basically means that the colorization was not doing something low level. It was actually doing something very high level. Because if you look at the training data, see, all these dogs have their tongues out. Okay. So it seems like what the colorization was learning is say, oh, this is a dog. If it's a dog, the tongue might be out. If the tongue is out, then now let me paint it pink. Okay. So it was actually doing a very high level task. It was actually recognizing dogs just so it could color it, which is exactly the idea of self-supervised learning. You give it some pretext task that you may or may not be interested in, but you hope that through that task it will learn something more fundamental about the world. And indeed, we can do a little bit of a deep net electrophysiology, so we can poke some neurons inside of the representation and see what they fire on, what those neurons are excited about. And you can see that here we found a neuron that fires on sky, trees, water. There is other neurons that reply, that notice faces, dog faces, flowers, right? And all of this from a very, very simple low-level task of colorization. So this is quite interesting. Okay, and we have done other similar tasks. We predicted holes in images and other tasks, and all of them kind of show you that it's learning something interesting. Okay, but the problem is when you are trying to predict pixels, it's actually pretty hard to predict pixels because it's a very high dimensional prediction task. So we can make it simpler by, instead of predicting high dimensional image, we can predict something very low dimensional, like a transformation. So we give two pieces of visual data, and all we need to predict is a transformation that actually relates between them. Okay? And here is one example. This is actually one of the first papers in self-supervised learning. We did it in 2015, of trying to do this kind of prediction self-supervised task. So here is the idea. Here are two patches that came from the same image. And the algorithm is asked to say, how are they related to each other spatially? So given that patch A is here, where should patch B go? Okay, so it's a problem, eight-way classification problem. But if you try to do it yourself, so usually, if it was a live presentation, I would ask everybody to ask, where should the other patch go? So where would it go? Well, probably it should go somewhere here, correct? And then I ask you, why? Why do you think that? And then somebody in the audience would say, well, because that's, this looks like the top of the bus, and this looks like the side of the bus. So now think about this. If you never saw buses in your life, if you came from from the jungles somewhere where you never seen buses your whole life, would you be able to solve this task? And the answer is probably not, right? Because what really happens is you look, okay, this looks similar to the top of the bus, this looks similar to the bottom of the bus, and then I can solve the problem. Okay. So now, by making the computer solve this frankly useless task, because to solve this task you need to know about buses, this kind of tricks the computer into knowing about buses. So this non-semantic task tricks the computer into learning about semantics. Okay, so here is how it works in practice. You give a random image, then you put a random patch in it, then you take 8 patches around it, and then you train a Siamese network to do this prediction, 8-way classification. You train this for, again, a month. And then the nice thing is at test time, you can now just take one of those neural networks, have one representation, and look at the embedding, at the feature that it learns. And one thing we can do is we can just look at the nearest neighbor. So given an input patch, what are the nearest neighbors in this deep representation that it has learned? And what you see is that basically it finds other cat heads, even though it has never seen any categories. It never saw any category labels. It was only trained on one image at a time without any labels. And yet, because of context, it's learning to use context to group together different cats together. Okay, and that's kind of impressive. This is a surprising result, right? That you can get something semantic, some idea of kind of going from instances to a category to emerge from a very low level task. Okay, and so we have, since then we have tried to play around with a lot of other pretext tasks for various self-supervised tasks. This is a kind of one example that I think is kind of a little bit different, where we kind of go back and try to go back and see if we can do self-supervision for multi-sensory signal. And the motivation from this comes from this psychology experiment called the McGurk effect. So now I'm going to play an audio, and I want you to tell me what the guy is saying.
Ba, 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 ba.
Okay? So hopefully most people have heard him say ba, B-A. Okay? Now let's do another experiment.
Ba, 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 ba.
Okay, so most people, at least English speaking people, hear the guy say fa, F-A. Yes, I hope that you guys have heard F-A. In reality, the audio is exactly the same. He's saying exactly the same thing. I just switched the video on you. Okay, so it's the same audio, different video. So he looks like he's saying fa with an F, and your mind hears fa, even though the audio did not change at all. Okay, so this is a remarkable result called the McGurk effect, and it suggests that there is a very tight coupling between the audio and the visual streams. Okay, and this is not true in computer science. We treat them as completely separate things. Okay, and so we were motivated to see if we can connect the video representation, the audio representation in a tighter way. And so we came up with a multi-sensory representation that would both take audio and video, and we wanted to make them tightly coupled to each other. And we thought we will do this using self-supervised learning to force them to connect tightly. Okay, and what we did is our first idea was to basically train a classifier to say if a pair of audio and video is real or fake. So, for example, here is a real sample that we got from the internet. Okay, it's audio and its corresponding video. And then we needed a fake one. And for fake one, we first thought, okay, we could just take another random video from some bag of videos and then just play its audio clip. Okay. Okay. Now, the problem here is that this task is just very, very simple. It's too simple. Okay. It's very easy to tell that this audio doesn't go with this video. You don't even need you don't need a video for it. Just a single image is enough to say, okay, there are no cars. It's indoors. Okay, it's wrong. Okay. So we thought, okay, we need something a little bit harder. So our second idea was we're going to keep the same audio, but we're going to shift it a little bit in time to make it not correspond. Okay, now you can see that it's much harder, right? In fact, what you need to do is you need to find a correspondence between an audio and a video and realize that they are shifted against each other. It's not a trivial task, and it's a task that needs a lot of concentration, and you do need a video for that, okay? Because even for humans, you need a couple of seconds to figure it out. So basically that's what we did. We trained a network to do this task, basically, binary, aligned or not aligned. And then once we trained it, then we could actually visualize which pixels are responsible for sound by basically just visualizing the 3D class activation map to see which pixels were responsible for saying if the video is aligned or not, and just running it on real imagery. And I will play it to you, and it will highlight the areas of the image where it thinks the pixels were responsible for the sound. Okay. And also we thought, oh, we can also do a little cute application of separating the on and off screen source of signal. So since we have a way to tell which pixels make sound, we can, let's say, take a video of somebody speaking with an interpreter and separate the audio, kind of going the other way, separate the part of the audio that has evidence in the pixels from the audio that does not have evidence in the pixels. So it's taking an image like this, or video like this.
Were able to show to the rest of the world the unshakable Japan-US alliance.
Thank you so much.
Okay, and now we can take only the audio that has evidence in the pixels.
夢の揺るぎない絆を世界に向かって示すことができたと思います。Thank you so much.
Okay, or we can do the other way. We can show only the audio that doesn't have evidence in the pixels.
Were able to show to the rest of the world the unshakable Japan-US alliance.
Okay, so that's for transformation prediction. Finally, let me talk about what I call meta supervision. Okay, and meta supervision, to kind of to understand what I mean, is the direct supervision is something like this. Given function f of x, we give it a label y, and that's basically what f of s should return, right? Very kind of strict. A meta supervision is when you have a f of x and you don't know exactly the label y for that, but maybe you say that it should be maybe in a set capital Y of things. So you kind of supervise it with not one thing but with a set. And GANs, for example, is a great example of meta supervision. Okay, so what do I mean by this? So for example, in a bunch of image-to-image translation tasks, for example, colorization or super resolution, if your objective is to just make, kind of regress from grayscale to color, or regress from low resolution to high resolution, the results are very blurry, as you can see. Well, here they're very blurry, here they're not very colorful, okay? Because L2 regression kind of averages everything, so you don't get a very sharp result, okay? So this doesn't really look like a kind of a real good image. And so what we would rather have is we would want to have some sort of a unified loss function that would just make good looking images, okay? For any sort of kind of a image task, just make a loss that says, this image looks good, okay? So how do you do this? Well, we can do it with humans. We can basically have humans in the loop, and we can give the humans a whole bunch of real images, and then the humans can compare the images produced by a network and real images, and then if they cannot tell the difference between the two, that means that your images are doing a good job. But this is not something you can put inside of an optimization of the algorithm. That would be too expensive. So the idea of generative adversarial networks is to basically, instead of humans, have another classifier, right? It's a classifier that's sitting here And it's basically trying to tell if the output of our first network is good enough to be confused with real data. Okay? And as a result, it basically teaches you what looks real. Okay? So, for example, again, in the colorization example, you have an image, you have a network that turns it from grayscale to color, and then you have another network, a discriminator network. So this one is a generator, this one is a discriminator, who says, is this look real or fake? Can I discriminate it against a real image? Okay, so the generator tries to synthesize fake images that would fool the discriminator, and the discriminator tries to identify those fakes. Okay, so this is a kind of a classic minimax adversarial optimization problem setup. These G and D are kind of fighting against each other. It's quite hard to optimize, but if you are successful, then what you get is you get kind of a very neat thing, because from the point of view of G, D is now kind of like a loss function. It tells you basically the objective. It tells you what looks correct, what is a good way, what makes this image look real. Okay, but it's a loss function that's learned for every particular task. Okay, and this turns out to be a very powerful result, because then it allows us to basically, for any given problem, we can just learn this kind of a set supervision that says, make it look real. Like, I don't know what the correct answer here should be, but just make it real. And that's basically what GANs do. They project your data onto a manifold of, let's say, set of real data. Okay, so this was the intuition behind our pix to pix approach from a few years back, where we basically kind of allowed a universal image to image translation from any inputs to any outputs, and the network basically learns the right loss function to output output correct results. And it was really nice because we put the result, the code online, and within a few weeks, people just started doing various wonderful results with it. And there was lots of cats, because the internet is full of cats, but also real artists starting to use the software to get some really amazing results. So this is Scott Eaton, and he basically put it into a sketch interface, where he took a bunch of uh, photographs of nudes in his studio, and then he trained it with their boundaries. Okay, and then he used that to then apply it to a sketching interface, and I'll show you just a little example of his system in practice. So here is his sketch that he's sketching, and now you can see the network basically hallucinating this crazy, surreal human forms out of this sketch. Okay, and it's really amazing, because it's able, it's getting the shading right, it's getting the kind of the feel of the skin right, even though it's just this very simple translation problem. It's not trying to do anything very sophisticated, but the results are, I thought, very, very impressive. Here's another example. So it was very nice to see artists be able to use the output of our geeky computer vision. Okay. Another type of meta supervision. So we talked about, this is direct supervision. F of X is in the set Y is GANs, but we can have other types of meta supervision. For example, another one that I'm a big fan of, that we did a lot of my lab, is we call cycle consistency. Okay, and here is the constraint. The constraint is, we don't know what F of X should be. Okay, we don't have that information, but what we know is that G of F of X should get back to X. Okay? And this turns out to be, it's a very weak constraint. It's a very weak supervision, but it turns out to be surprisingly powerful. And that is what's underlying our cycleGAN result. So here we are going to translate from, let's say, a set of horses to a set of zebras, but we don't have pairwise labels. Unlike in Pix2Pix, where we always had pairs, here we don't have pairs. Okay, so we only have set level correspondence. And so what we do is we say, okay, let's train a translator from X to Y, from domain X to domain I, but we can also train a backward translator to go from Y to X. Okay, and here it's basically like the intuition is with language. So let's say that you only speak English, and then you want to write a love letter to your girlfriend who is French. Okay, and you don't know French, so what you do, you use Google Translate. You translate it into French, but Google Translate is not perfect, so it might be wrong. So what you can do is you can translate it back to English and see if it says what you started with. And if it doesn't, then maybe you update, you change your letter a little bit so that it becomes consistent, cycle consistent. Okay, and that's exactly what we're going to do in the visual domain. So we start with a horse, and then we translate it to a zebra. Okay, but we still don't know if this is a correct zebra or not. So then we can translate it back into a horse, and now we need to make sure that what we get here is similar to what we started with. Okay, and this is called the cycle consistency loss. It's basically just a reconstruction error. Okay, so, and then we do it the other direction as well for symmetry. Okay, and that turns out to be extremely powerful. And so here is an example of just doing it one frame at a time. We also can do it to translate my photographs in Paris or to Cezanne paintings. We can also do something that nobody has done with except for us, and we can take paintings and actually translate them back into photographs. Okay, because we have both of those networks available, so we can just use one or the other. Or we can translate from computer graphics to real imagery, or you can do it the other way around to make your world look like a game. And of course, even the failure cases are not bad. I showed this when I gave a talk in Moscow, and everybody really liked that. So let's see. I want to save some time for questions. So I will, let me show you one last thing, and this is basically kind of using the cycle consistency as a way to do motion transfer. Okay, so here the example is that we have a video of my student Caroline, and what we want to do is we want Caroline to dance like a professional dancer. Okay, and so what we can do is we can make a cycle with kind of a asymmetric cycle. So we can basically take this stream of video, translate it into poses, and this is actually, you can do this. There's software on the web. OpenPose is one software that does it very well. A wonderful research out of CMU that can translate a video stream into poses. Okay, and now that you have the poses, now you can take this image and train a Pix2Pix network to translate it back into this video stream. Okay, so now you have a cycle of video, poses, back to video. Okay, and you can train this for a long time. Okay, so why is this useful? Well, it's useful because you can train the cycle at training time, but at test time, what you can do is you can change the beginning, and you can break the cycle and make it go from a dancer to our Caroline. And I will just play you this, okay? Okay. And maybe one last little thing, that you can do this kind of cycle supervision, not just in space, not just between domains, but also in time. Okay. And so we had a couple of papers that tried to do this for the task of finding correspondences between visual data. So basically, to figure out that this is and this is the same dog, right? This idea of continuity is very important to humans, and basically the idea is to learn that this dog is the same as the dog at the beginning of the video. And the idea is to use time and to use cycles in time as this kind of supervision. And so what we do here is we start with a random patch in one frame, and then we basically track it backwards in time using a tracker that is basically has a deep feature that learns a distance between, basically learns correspondences between the different patches. Okay, so in the beginning, this tracker is basically random, but you go backwards in time. You don't have a label for where it should be here, but what you can do is that you can turn around and then track it forwards in time. And of course, what you want, if this tracker F, if the feature that it learns is good, you want it to end up at the same place. So this is our error signal. This is our delta that doesn't allow it to be a full cycle. And so what we need to do is we need to basically train the representation F such that this becomes smaller and smaller. Okay? And then basically that is you can use that to propagate the error signal back, propagate it back, and then train F to be better and better in this task. And here is an example of it basically converging as it's training over the iterations, basically getting better and better and better and better. And you can see that it's kind of it does what you want it to do. Okay. And this basically learns, again, with using self-supervision, a feature that corresponds between the different pieces of data. Now, there were some limitations to this approach because it was very expensive, one patch at a time. You only kind of track once, and it was kind of complicated. And so the paper we just presented at Europe's just now was to basically pose this as a random walk on a graph. Okay, so I'm not going to actually talk about it. I'm just going to give you a little bit of an advertisement here, but it's a very nice setup proposed by my student Alan here, that basically says, let's just take a random walk, just treat a video as a graph, but make the video a palindrome. So if you can see it, it goes from t to t plus k, and then it goes back to t. So that it's again, basically it's by construction there is a cycle. So you start at at exactly the same place. Okay, and then you basically do a random walk on this graph and steer it so that it ends where it started. Okay, and that turns out to be a very effective, a very simple way to learn a representation. Okay, so I'm yeah, if you're interested, very encourage you to look at the data. Okay, so I am basically going to finish here. So to conclude, the magic is in the data. Okay, the magic is not in the algorithms. You can have the best algorithms in the world, but if your data is not good, nothing is going to work. Okay, and the problem is that the machine learning methods, if your data is not right or your labels are not right, they're going to cheat. They love to cheat. And so we need to wait to make sure that our algorithms don't cheat. And something like self-supervision is a one attempt to prevent the algorithms from cheating by basically just giving it more and more and more of this supervision extracted from the real world. Okay, thank you very much, and I am happy to answer questions.
Thank you, Alexei, for the very interesting presentation. Our audience say I will read you some comments. For example, I love that this presentation is based on images. So we were watching really fascinated about your work. And there are also some questions for you. I will read them to you. The first one. What do you think about using such self-supervised models to generate fake data, such as fake news? Are you concerned about this?
That's a good question. It indeed, the GAN models that I talked about, they have been involved in some in some synthesizing, especially faces, or having faces say things that they didn't actually say. There is a paper called cycleGAN that's based on our work, cycleGAN, that you can look at as an example of this. Indeed, in my lab, we have had some work on trying to defend against this, okay, or at least detect this. So this year we have a paper that basically tries to classify if an image has been produced by a deep network or it's a real photograph. Okay. The good news is that right now we are very good at doing this. So, for example, for something like this image, our method would just be very certain that this is fake, that this is not real. Okay. So, for now at least, these methods are not. They may be sometimes fooling people, even though actually most of the time even that is not true. But they are definitely not fooling our algorithms so far. Okay. Now, and it turns out it's actually pretty simple to train a method like this. But this does not mean that in the future, in the future, these methods, the algorithms, the synthesis algorithms might get better, and it might get harder. So definitely there is a concern like this in the future. I am actually not that worried about visual fakes, not because it's impossible. In fact, it has been possible. Deep fakes have been around, or fake images have been around for a long time. Stalin had been doing fake images in the in the 1930s. Just with photography, right? It's nothing new, and they will continue to happen. And in movies, for example, something like Forrest Gump, the whole movie is one big fake. Um, I don't think I'm not as worried about this, because I'm much more worried about much simpler things. That some of the fake information that is being produced right now by regimes like the Putin regime, or frankly even Donald Trump in America, they don't need to be they don't need to do anything fancy with visuals. They just say things that are not true, or they type things that are not true. So I don't think we need to worry about the high technology solution, or high technology ways of generating fakes, because you can just say things that are not true, and a lot of your people are going to believe you, which is kind of much scarier, I think. So I think that's really the bigger problem right now than these sophisticated technological things. I think it's a sociological problem before it's a technology problem. But for technology, we should be able to find ways to combat that, and we're definitely working in that direction.
Yeah, so in fact, the problem might be much, let's say, as you say, less technological, more hidden in people themselves.
Exactly. People want to believe things even when they know they are not true. This is what we have seen. So, in one example that my grandmother was telling me is, she lived in Stalin's time, and when one or another party boss became was removed, uh, what they did is they put a big X on their face in official photographs. So it wasn't very sophisticated. People could see that, yeah, they removed it with like black ink, right? So it wasn't meant to be invisible to the people. It was meant to be like they knew that it was false, and they still believed it. And the same thing with the best liars. Some of the things that some of the politicians say, they know that they're saying what they're saying is false, and the people are also knowing it's false. And the fact that the people still believe it, even though they know it's false, is, I think, part of the power of this whole issue. And so, in that sense, making the fake very convincing is actually, defeats this thing. So I think it's a you know I think sociology, human psychology and human sociology are absolutely fascinating and quite scary sometimes. So I think this is something where we need to be looking at.
Thank you very much for your answer. Meanwhile, you answered the second question about using the models to detect whether the movie, for example, is real or fake.
Mhm.
So let's keep that one and go to the next one. How come those sketches are filled in interactively? It was about the slide with the
Oh yes,
drawing.
the Scott Eaton. Um,
Yeah, how did you do
so
it?
well, actually, for that one, I'm not quite sure if it was really interactive or he just visualized it interactively in his presentation. So you should go to Scott Eaton. You Google Scott Eaton artist. I think he lives in London, and you can look at he has a wonderful full length talk about his process, how he does this, and so you can look at that. But the pix to pix software is actually very fast. You can run it interactively. In fact, if you Google for edges to cats, edges digit 2 cats, there is an online demo that's almost real time, and this runs in your browser. And if for other things, you could make it real time, because it's very fast. Its training is slow, but at inference time, the neural networks are actually extremely fast. So you can actually do it on the fly.
Thank you very much. Next question. What, in your opinion, would be the next impressive task for self-supervision to solve?
So this is a typical graduate student question. All the graduate students come to the professor and say, "Oh, what's the next big thing?" And it's kind of a weird question, because of course everybody will tell you that the next big thing is exactly what they are working on, because otherwise why would they be working on it? Because they think it is the next big thing. So I I think what I'm interested in is I'm interested in video. I'm interested in using self supervision to understand visual video signal. We don't really have very good motions models of video, and I'm also interested in in having, instead of designing these prediction tasks, I want the computer to kind of to infer on its own the right prediction task. Okay, so that's the kind of things that I'm interested in. But you know, you can look on my webpage, and all my latest papers are the things that I think are the next big thing. But we will see. Time will tell.
Okay, thank you very much. And the last one. Self-supervised learning seems to be sensitive to input transformations, which looks a bit like handcrafting what kind of semantics a network needs to learn. What works on the ImageNet classification downstream task may not work on other downstream tasks. I wonder if you think this is a problem and if you have any thoughts on how to tackle it.
Very good question. That's exactly my worry. So one of the type of self-supervision that's been very popular right now is something like SimClear or other works like this that use contrastive learning to bring an image closer to other images that are automatically transformed with something like data augmentation. I This is exactly why I'm not a big fan of these methods, because the transformations, by deciding what transformations to use, you're basically putting in supervision. So the last thing I briefly mentioned of this doing random walks on a graph is in a way an attempt to get away from that. Okay, so basically what we're doing in that paper is we're using the video to suggest to us the transformations to use for contrastive learning. Okay, so instead of coding it in by hand, we're learning those transformations automatically from the video. And I think that's a much better way to go, because because it basically it removes the human from this decision process. So if you're interested in this, so this is definitely one paper to look at that tries to get rid of this kind of data augmentation part. Yes.
Thank you very much for the answer, and thank you for your presentation. Short announcement for our audience. Now we will have the closing remarks of the official part of the conference, and we invite you for the unofficial one, which will last, let's say, at least 2 hours. Networking, pub quiz, integration. So stay with us, and see you later. Thank you, Professor, once again, and
Thank you.
hope you join us as well for the integration.